So let's do the vector wave equation case. Okay. So again, you have two regions, region 1, region 2, B1, B2. They might have epsilon 1, mu 1 in region 1, and then epsilon 2, mu 2 in region 2. And you write down the vector wave equation in region 1, which would look something like this. But you're assuming that region 1 is homogeneous, so you can actually have a dyadic Green's function that you can associate with region 1. Okay. And then region 2 is also homogeneous but with a different wave number. Okay. With a different wave number. Then you can write down the dyadic Green's function in region 1 and 2 as we did for the scalar wave case. But then the vector algebra is a little bit more complicated. You go through the same kind of exercise as you would do. Okay, but then the trick about dyadic is a little bit complicated. You cannot simply multiply from the left by G1, G2, and so on, because the order is very important. And if you have problem working with dyadics, the best thing is that you multiply this equation with an arbitrary vector A. You multiply this equation with an arbitrary vector B. A is a constant vector. You convert all the dyadics that you have into vectors. Then you can multiply. Okay. So what you do then is that you multiply this equation from the left with the dyadic. I can put the A, I can not put the A, it doesn't matter. I can multiply this equation with the dyadic from the right. But then because of the way the A's and B's are ordered, I have to multiply this equation with E1 from the left and E2 from the left. Okay, if I look at this equation, again I have to multiply by E2. And then you do the same trick as we did before. This equation, subtract this equation, the middle term will disappear. E1 omega squared mu1 epsilon 1 G1 will cancel this term over there.
Then what about the A?
The A, you can put them back, right? I say they are there for you to help you to think. If you can't think dyadic, you can only think back within the A. If you can think dyadic, you can throw them out. But when you think dyadic, remember the order is very important. The order is very important. So you can put them back there if you want to. And then you subtract them, they will also disappear, cancel the A later on. But you can kick them out, since all of you know how to think dyadic now. Okay? So you subtract the two equations, and then you get this horrendous looking thing that is very complicated. Like E1, like you have things like curl cross E1 dot G1 minus E1 dot curl cross G1 kind of thing. And then if you don't want to think dyadic, you can still put back the A there. Okay, you can put back the A there and convert those to vectors. Then you have to look for a vector identity for this. This can be written as a divergence of something. This is a vector. This is a vector. So this is equal to divergence of A cross B. You identify what A and B should be. Okay, and then this will be the divergence of maybe C cross B or something. Okay, you can identify what the C and D should be. And what is the divergence of A cross B that you remember from the chain rule? Divergence of A cross B, B dot curl of A minus A dot curl of B. Okay, remember this minus sign is very tricky. That minus sign is not there in the chain rule for gradient or divergence of scalars, but divergence of the vector, you have to remember that minus sign. And then if you use this, then you can convert this into a divergence of something. Convert it very much like Green's theorem. Then you apply Green's theorem in the vector form, which we call vector Green's theorem. I don't know if George Green was responsible for this, probably not. Because all these vector things didn't come about until later. So the vector Green's theorem. And then if you do that, then you go through the algebra and then convert things into surface integral. This allows you to convert things into surface integral. Okay. And then you end up with things that look like what we had before. Again, you use the argument that things will look like plane waves. When you're very far away, the integration over S infinity goes to 0 because there are two terms that cancel each other because they look like plane waves. Okay. And then this gives rise to a form where the field is always to the left of the dyadic Green's function. You find that the field is always to the left of the dyadic Green's function. That's not pleasant because we always write the dyadic Green's function that acts on something. Instead of acting something on its left, we want it to act on something to the right. So you always end up with things that look like this in this manipulation. You end up with, say, if I just take this term over here, I will end up with things that look like this. dv j of r dot of g of r prime. I will end up with something like this because of the mathematics. And this is unpleasant. I can change this so that this becomes on its right by taking its transpose. So by taking its transpose, you can prove that dyadic Green functions always satisfy this relationship. If you change the order of the arguments, it's the same as transposing the dyadic Green function. That can be proven by reciprocity. You can also prove that the curl of the dyadic Green function, which is related to the magnetic field, and if you take the transpose of this diode, is equal to minus the curl of G, 1 of R prime R. There's a minus sign involved. Okay? You make use of these vector identities, then you can convert that all the field quantities now are always to the right of the dyadic Green function. You have the form that you see in textbooks. And you have this vector form of the integral equation. You have the extinction theorem also, very similar to what we see here. But what is the thing that gives rise to the discontinuity? Say if you write everything in terms of the E field, you'll find that the E field is discontinuous across the interface. So what gives rise to a discontinuity in the E field? What kind of surface forces would you have in this problem?
So surface current.
You have surface currents of the electric type and the magnetic type. I don't want to go into the detail because it's written up in the textbook, but what you have are terms that looks like this. Okay? Like once you apply this divergence theorem, you have terms that looks like this. Okay, you have terms that look like that. Okay, because of the convergence or converting of the volume integral into a surface integral. And then you can use vector identity and write this as this. Okay, across G. You can always write it in this manner. And this is just minus M1, the surface magnetic current. You can think of, if this is a surface force, it will correspond to a surface magnetic current. And then there are other terms that will correspond to surface electric current. Okay, I would not bother to write out those terms. Those terms will have n dot curl of E1 cross of G1, for instance. You have terms like that, and by using vector identity, this becomes an H field, and then you will have n cross H kind of thing, dot G kind of thing, and this is like a surface current. So surface currents and surface electric current and surface magnetic currents will emerge to replace the monolayers and dipole sources we saw in the scalar wave case. In the vector wave case, they are replaced by surface electric current and surface magnetic current. Okay? But which of this surface current will give rise to discontinuity in the electric field? The electric field will also have some of this extinction theorem. Depending on where you are, the field suddenly jumps to 0. Depending on whether you are in region 1 or region 2. Go through the same mathematics. But which of the two currents give rise to a discontinuity in the electric field? Very good. M gives rise to discontinuity in the electric field. Because you know that J gives rise to discontinuity in the magnetic field. So M must be the one. Okay. And extinction theorem is caused by the jump condition we need to impose across a magnetic surface current. And you have things like this. Okay, that is the essential physics that you see there for the vector case, except that the algebra is maybe a few times more complicated than algebra. But the physics is very similar. Physics is really very similar. And then you can have four equations, four unknowns to impose boundary conditions. Impose boundary condition that tangential E is continuous, tangential H is continuous. So the surface magnetic currents that you have, inside and outside, have to be equal. But what we are actually deriving here is actually the equivalence principle. That is in Harrington's book. You never show it mathematically, right? You just say that if I put this current here, put this current there, I get the total field outside and zero field in certain regions. If you read Harrington's book, you will have this equivalence principle that you just intuit. Use intuition to argue that if you have this current, it must give rise to zero field inside and in certain region. And he calls those equivalence principle 1, equivalence principle 2, equivalence principle 3. But all this actually follow from the extinction theorem, vector Green's theorem, and so on. And also from uniqueness theorem, I suppose. If you go to this, everything is logical and mathematical. Even this is logical and mathematical. But you can also use intuition to argue that the answer has to be such. For instance, if I have some source over J, it produces E and H outside. Okay? What the vector Green's theorem tells you, you can go through the mathematics. You can actually show by the mathematics that if I have a surface over here, and then on this surface if I impose J is to the n cross H, M is equal to E cross N, for instance. Okay? Then this current actually produces the current that exactly cancel the incident field. I can call this incident. The field actually can be shown to be 0 in here by the same kind of derivations that we have shown. Okay, these two sets of current will produce exactly the same field that cancels the incident field, so the total field is 0. Another way of saying it is that these two currents, if I were to flip the sign of the normals, okay, if I were to flip the signs of the normal, it produces exactly the incident field that was originally there before I put in the equivalent surface. Okay, so if I put, say, Js is to the minus n cross H incident, Ms is to the minus E cross incident, if I flip the sign of the field in here, it will be exactly like the field before I put in the equivalence current. And then this surface current radiates field only in one direction. It reproduces the incident field here, it gives you 0 field outside. You can argue this by the uniqueness principle that if I have such a set of current and 0 field outside, the only way the boundary condition can be satisfied is that the currents have to be equal to this number and that number from the uniqueness principle. And I don't have to invoke any Green's theorem or very long mathematics, so I can use intuition to argue that the equivalence principle has to be such. It's kind of hard to catch, you have to think about it. But mathematically it's very logical. You just go to the machinery of cranking, and cranking, you get the same conclusion. But here you have to use intuition. Okay, yes?
Before when we said charge and dipole, we said dipole gives discontinuity. Was that just for the static case that the dipole introduces discontinuity?
The dynamic case also. The dipole
no, for the dynamic case, both of them produce discontinuities, right? Not just dipole term?
No, only the dipole layer produces
term.
jump discontinuity. The monopole layer term produces the field that looks like this, right? The dipole layer produces a field that looks like that.
So that's true in statics and dynamics?
Yeah, because you are near to the source, essentially it's a static physics. You put your observation point very close to the surface. You observe electrostatic physics and magnetostatic physics. So whatever argument that you use for electrostatic and magnetostatic should also hold true for electrodynamics.
Doesn't J and M produce discontinuities though?
J produces the discontinuity in the magnetic field. M produces the discontinuity in the electric field. Okay, not in both fields. Okay, so the equivalence principle also follows from here. I will not elaborate that. Any further? Are there any questions so far? No questions, right? So then we talk about the volume integral equation case. The volume integral equation case is the case where you don't have constant, say you have K1, K2 is the function of position, is an inhomogeneous medium. Then you have this equation to solve. Or maybe I can just say VR is equal to that. I have this equation to solve. I can do this by finite element method also. I can put this in a mesh it up, and then find the projection of this equation into a subspace, convert this into a matrix equation, and solve this equation. But then it does not satisfy radiation condition. In order to satisfy radiation condition, I have to put in a atomic boundary condition. I can also use Green's functions technique to solve this problem. So I define the Green's function for the background. Maybe I call this the background Green's function. Okay, maybe I don't have to carry this background. Just this Green's function satisfies this. Where kb squared is equal to k1 everywhere. So kb squared is equal to k1, but it will be not equal to k2 in region 2. And how do I convert this into a volume integral equation? I can convert this into a volume integral equation by doing tricks like that. I rewrite this equation so that kb squared phi of r is equal to q of r. And then I put kb squared. I have a kb squared that was not originally there. What's that? kb is the background wave number. It's equal to k1 outside the scatter is equal to k1 also inside the scatter. It's a constant everywhere. Just assume that it's a constant everywhere. Okay? This, you can also think of it as k1 squared. Sorry, this would be k1 squared everywhere, right? And then I can convert this equation into a integral equation by using the principle of linear superposition. If a point source produces this Green's function, these are distributed sources. These are distributed sources. And this thing, what is this thing equal to outside the scatterer? 0, right? This thing is 0 outside the scatterer. Because I define kb to be k1 outside the scatterer. K squared is this number here, which is equal to k1 outside the scatterer equal to k2 inside the scatterer, this k squared. Okay, this is an inhomogeneous medium k vector, or k number. So I can think of this as distributed sources, but this source q is somewhere out here. And then this is somewhere distributed sources inside the scatterer due to this difference not in 0. So I can use the principle of linear superposition and write the fact that phi r must be equal to minus g r r prime convolved with q r prime. Okay, the volume of the source. If we call this V source. Okay, there's the first term. And then the second term is only non-zero on the scatter. There should be a dr here. Okay. This should be on V. Okay, it's only non-zero on V, and then gr r prime k squared minus kb squared phi of r prime. I just put a minus sign. And then this is an integral equation because this is known. And then this is unknown. This is unknown. This is a linear operator equation. So I can write this as a volume integral equation where the unknowns are inside the volume of the scatter. Okay. I can put R belonging to V. Then the unknowns inside the integral is distributed on V, and the unknowns outside the integral is also distributed over V. So they are the same set of unknowns both inside the integral as well as outside. So I can think of this as just the incident field. This is the incident field that is there before I have the scatterer. This is the incident field. This is a scattered field due to the presence of the scatterer. I can think of this as a scattered field if I want to. And the scattered field is due to induced sources. These are induced sources created in the volume. Okay? Induced sources created in the volume. So you can write this as phi of r is equal to phi incident of r minus an L operator operating on phi of r prime. You can think of this as a linear operator equation in this manner. And then you can rewrite this as identity operator plus L times phi r prime is equal to phi incident of r. Okay, and then you can, this is a linear operator equation. You can use subspace projection method, use basis functions, expansion testing functions, convert this into a matrix system, and solve the matrix system. Okay, things that we have learned in chapter 5. And then you have a set of matrix equations to solve. You can repeat this for vector wave equation. And again, the physics is very similar. Physics is very similar. You have incident field, you have a volume current term. You will have integration over the volume of the object due to induced sources in the volume. Okay. And it's written up in the textbook. You can read about those. The details are in the textbook. But the physics is very similar. Are there any questions? Yes?
This equation, the second kind of.
Oh yeah, this is called the second kind. Very good. This is called the second kind integral equation. When you have identity operator as such, it's usually called the second kind, because you essentially have the unknowns inside as well as outside the integral operator. Okay, this is called the second kind integral equation. The mathematicians sometimes define the second kind integral equation quite differently from us. They will define second kind integral equation where you have an operator here, where the domain space of this operator and the range space of this operator are the same. Because this is an identity operator. Okay. Whatever you have in the domain space will also be have in the range space. And then when this is compact, if this is compact, and then this will be an operator that match from one space to another space, and two spaces are the same because of this identity operator. Okay, the two spaces are the same. And that would be called the second kind integral equation. There's another definition of second kind integral equation. Then if you have a integral equation like this, like what we have over here, then there's something called a Born approximation, which is quite well known, a Born approximation, which states the fact that this is a scattered field. If the scatter is weak, so that this is much smaller than phi incident. And the scatter is weak, so that this statement is true. Then we say that phi is approximately equal to phi incident. Okay, in that equation. And then if you make the approximation that the total field is the incident field with the integral operator, which is this operator over here, operating on the incident field, that is called the Born approximation. Okay, it's called the Born approximation. It's used in quantum scattering quite a bit. It's used in a lot of remote sensing applications. It's used in a lot of applications where you can argue that the scattered field is much weaker than the incident field. You can make this kind of approximation. It's used a lot in inverse scattering too, in synthetic aperture radar, in a lot of different technology.
What's the significance of, like in the top equation, you have the second order. It's an integral operator over all the scattering sources, like the field at kind of the scatter.
Right. This is, I should say, R prime is in V. Here over R is in V. Yeah. So the set of unknowns outside the integral, as well as inside the integral, are the same set of unknowns.
Okay, so that's what lets you rewrite the left-hand side of the next equation in terms of just VR prime.
Oh, this is an identity operator. And if you think of this identity operator as an integral operator, it has a delta function in it. And then I can put this as VR prime. Okay, you can think of this as, if it has the same footing as an integral operator, it will look something like this. Okay, it will have that term in there. So, what you see here is that when you have integral equations, also you can do one approximations for vector wave case. Okay, vector wave case. I will not go into the detail, but it's written up in the textbook. Very similar kind of ideas. If the scattered field is weak compared to the incident field, then you can make this kind of approximation. There will be constraints restriction. Restrictions on when you can apply one approximation. That usually is the case when the scatter is small. When the scatter is a weak scatter, when the homogeneity is not very different from its background. If K2 is very close to K1, okay, one approximation goes very true. Or if this scatter is very small, very, very small, so there is a weak scatter, then one approximation also goes through. Okay, you can read the textbook more on different restrictions on as to when you can make one approximation. Okay. So we see that in a surface integral equation case, you have phi of r is equal to phi incident of r plus or minus the s prime n dot. Let me see what I have. For the surface integral equation case, n dot gradient of phi1 r prime g1 r prime minus phi1 r prime n dot g1 r prime. Okay, you have that thing open. And you have two kinds of sources over there. If the surface is very hard, in the language of acoustics, okay, if the surface is very hard or very soft, then one of the two terms can be dropped out. Okay? Or in the electromagnetic language, when the object is a PEC or a PMC, then one of the two terms will drop out. If you have a PEC, n cross E is equal to 0. No magnetic current on that surface. If you have a PMC, n cross H is equal to 0. No electric current. So the equivalence of this for electromagnetic case, one of the two integrals will also drop out. Because one will correspond to surface electric current and surface magnetic current. So when we have a very hard surface, what does that mean? It depends on what this potential if this potential is the pressure in acoustics, okay, if it's the pressure, then if it's a very soft surface, then the pressure should be 0 on the very soft surface. Okay, then if the surface is a very hard surface, then it turns out the normal derivative of the potential on that surface is 0. Okay, so one of these two terms will also drop out, depending on whether it is a hard surface or a very soft surface. Okay. Or for the Schrodinger equation case, maybe it's slightly different. It corresponds to something with a very strong effective mass and something with a very small effective mass, and if you have a big contrast at the heterojunction between two semiconductor regions, one of the two terms can be dropped out, but one of the two terms would be dropped out. So let's assume that this is equal to 0, so that we don't have to deal with this dipole layer case. Then you have an integral equation that looks something like this. So this is a very simple equation, just one set of unknowns now. This is for, say, a soft surface. Okay? Soft surface. That P1 represents the potential. P1 is 0 on a very soft surface. And that so you can think of this as a problem involving only one unknown, and you can apply the extinction theorem, and that this should be equal to 0. Okay, does this